First of all, I would like to thank the organizers of this online conference. I'm Elkhaoui from University Sidi Mohammed ibn Abdullah, Faculty of Science, Dahar Mehrez, Fez. The topic of my presentation today is phase behavior study of a mixed system composed of a microemulsion with a polyelectrolyte, polyacrylic acid. Firstly, I will give you an introduction about our work. Secondly, I will present the studied system. And thirdly, I will present our results and discussion. And finally, I will end by small conclusion and perspectives. The purpose of our work is to study the effect of polyelectrolyte addition on the properties of an oil in water microemulsion of weakly charged spherical micelles. So for this study, we made phase behavior of a mixed system composed of a microemulsion with an polyelectrolyte acid PAA. So we start by the phase diagrams in an acid medium at pH equal 4.5, and after the phase diagrams in a basic medium at pH equal 12. And now I present the components of studied system. The first component is the macroemulsion. The macroemulsion is a thermodynamically stable dispersion of nano-oil droplets in water surrounded by a film of surfactant. The case that will interest us is that of macroemulsion consisting of oil droplets in water. There is a lot of application of the macroemulsion like agrochemicals, food science, biotechnology, cosmetics, pharmaceuticals, and others application. Surfactants consist of a hydrophilic hide and a hydrophobic tail, as you say in figure number 1, and at low concentration these molecules are soluble in water, but from a critical concentration they combine to form small aggregates are the micelles, as you say in figure number 2. And for the components used in the macroemulsion, the first component is ionic surfactant estrogen 100. It has like a molar mass of 624, and the co-surfactant used is octanol. Its molar mass equal 130, and the ionic surfactant used is the chloride CpCl. Its molar mass equal 329, and for the oil used is decan, and the last component is the distilled water. And after the preparation of the macroemulsion, we have added the polyacrylic acid PAA to the macroemulsion, and this polyacrylic acid is a weak acid with the molecular weight equal 250,000, and its monomer mass equal to 72, corresponding to 3,478 weak acid groups by macroemulsion. The weak acid character implies that its charge density is controlled by the pH. At low pH, the polyelectrolyte is weakly charged, whereas at high pH, a larger fraction of monomers are dissociated and the polymer charge saturates to its maximal value. And as you say in figure number 3, not all its groups are acid. There are some impurity in form CONA. That's why we studied the purity of this polymer to calculate the ionization rate of polyacrylic acid. And before sample preparation, 5 control parameters of the microemulsion are calculated. The first parameter is omega. It is a parameter to adjust the curvature spontaneous C0. It's equal to 0.4. And the second parameter is gamma. This parameter defines the mass ratio of oil compared to the surfactant and the co-surfactant. And the third parameter, it's psi, present the mass fraction of polymer. And the parameter number 4, it's delta, present the weight ratio of unique to neutral surfactant. And the last parameter, it's phi, present the microemulsion weight fraction. So the phase evolution of the samples with the number of charged pair drops is displayed in these phase diagrams at pH equal 4.5, and the weight ratio of PAA to drops is fixed and equal to 0.05, and the vertical axis is the weight fraction of unique to neutral surfactant. So for low charge addition, the solutions are monophasic and transparent over the whole range of droplet concentration, often increasing the number of charges per drops. One observes an associative phase separation similar to the one described above. A clear dilute phase coexists with a more concentration and a viscous phase containing almost all droplets and PAA. So when the density of the charge increase, electrostatic bonds between the unique surfactant and the carboxylic groups become possible. As described above, the repulsive interaction is progressively wiped out and replaced by an attractive interaction leading to the observed phase separation. So at pH equal 12, all the acidic groups on the PAA change are ionized and the polymer is fully charged and in its most expanded state due to the electrostatic repulsion between the neighbor charged monomers, and the charges on the drops allow for bonds of electrostatic origin. The partial phase diagram of mixture of charged oil in water droplets and PAA has been determined for pH equal 12, and as a function the weight fraction of unique to neutral surfactant and of the microemulsion weight fraction. The determination was again made visually on this phase diagram. Summarize the observation. For low charge densities, the solutions are monophasic and transparent over the whole range of microemulsion concentration, whereas these are biphasic at higher charge densities, often increasing. On one again observes a phase separation between a viscous phase and liquid phase, and also for low drops concentration the phase separation appears for larger charge density. So to conclude, at pH equal 4.5, the phase separation is between two phases, viscous phase and liquid phase, and at pH equal 12, the phase separation is between two phases, oily phase and liquid phase. And like perspective, simple preparation to draw a phase diagram in acid of pH equal 2 and study the dynamic of these systems by dynamic light scatters DLAs. Thank you for your attention.